see what. Oh well. So we're going to first start with the just general definition of what it is, then find a way how we can get those conditions met. And then I'm going to kind of focus on the Lorentz system of equations, which defines like certain convection currents in atmosphere and in water when you have a flow between two differentially heated plates. And then I'm going to kind of focus on that and then say how it relates to turbulence. And yeah, might not have too much new information, but I'll have some fun videos and stuff. All right, so chaos. What is chaos? Let's see. So first of all, yeah, it's sensitive to initial conditions. So we have a system that is based on several parameters, and it evolves like weather. And based on the initial conditions, the future evolution of the system will be determined. If you have a slight perturbation to the initial conditions, that evolution will change, and actually the different orbits will diverge exponentially. Then also you have, yeah, aperiodic long-term behavior. So in long term, as time tends to infinity, you never settle to a specific orbit like that. It just keeps going randomly around, or predictably, deterministically, but randomly. So that doesn't happen. So it's deterministic. It's not just noise. There is, in chaos, in pure chaos, there is no random factors involved. So you can have chaos mixed with noise, but you don't have to have it. And yeah, actually, I think like lately there's been some studies about actually like resonating chaos, driving chaos systems with noise. So it's pretty cool. You can actually get order out of two disordered systems. So that doesn't happen. And topological mixing, so yeah, there is no specific definition for chaos still accepted. So these are kind of all things that you need, but they're not necessarily exclusive. And there can be other ones, but they're not all necessary either. So topological mixing is another one. If you evolve to regions of space in time, eventually they will mix. Kind of like that. In the natural sense, there's a formal definition, but I won't go into that, partly because I haven't looked at it. So I'll start with simple 1D-dimensional systems, nothing fancy. We have a single differential equation that defines this. So it's a derivative equals to a certain equation. Here's the plot. Now, how do we look at this? How do we analyze it? We know that at this region, the derivative is positive, and therefore your value is going to increase. Whereas here, it's going to decrease. So this is a fixed point. If you're sitting right there, it's going to stay there. And from the region around it, it's going to actually flow into that point. So you have an attractive fixed point. Here, you have the same thing, but opposite. So that's a repelling fixed point, unstable fixed point. So if you're exactly on that point, you are going to stay there. But if you're differentially away from it, you're going to move away. And here's another attractive fixed point. So that's essentially what the dynamics of this system will look like. And you can see that if you are to the left or to the right of this point, like differentially small to one side, your orbits will diverge very quickly. But you kind of can't call this chaos because there is no aperiodic orbits or anything. Let's see, another thing you can do with this is you have a parameter beta that you can vary. So if you vary that, you're kind of effectively going in a two-dimensional system because you have two parameters now. But that's what you get. So if you have a small beta, you get essentially a tangent plot, one attractive fixed point. As you increase beta, you get to this. So essentially, this attractive point eventually splits into two. So again, based on your initial conditions, if you're slightly to the left or slightly to the right of this, you will go to one of these points. So that's called, as you're changing the parameter beta, so that's called a pitchfork bifurcation. So you have the stable fixed point based on the parameter, stable, and then it splits into two stables and an unstable one. You can easily see that with physical systems if you have like this. And I put a little bit of force squeezing it. Nothing happens. That's the stable fixed point there. If I put more force, it goes to one side. But it's differentially dependent on the initial conditions, which way it's going to go. So yeah, so this is now the stable point when I put more force. So that's kind of a physical example of this. And yeah, so these equations kind of create something like this. And in one-dimensional systems, you can have somewhat more complicated behaviors, but you can't get anything complicated enough to form chaos. And I spent too long on that. OK, in two-dimensional systems, it's still not very interesting because Yeah, you can easily have bifurcations all over the place. For example, right here, like if you extend these two, if it's slightly above or below the line, it'll go into different trajectories. So that's dependence on initial conditions again, but there is no aperiodic trajectories, mainly because in phase space, so any future of your evolution will depend exactly on the position in your phase space. So if you have a defined point, from that point, your evolution will be uniquely determined. So if you have any kind of an orbit, it has three things that can happen. It can either converge to a point, it can like diverge to infinity, or if it doesn't do either of those, it'll eventually have to cross itself, at which point you're back to the original point where you started, and after that your evolution is uniquely defined by the same curve, so you can't ever have anything changing, aperiodic. So that's the problem we have here. OK, so 2 dimensions isn't enough. So if we have a 3-dimensional phase space, we now have what we want. Because in that case, you can orbit around, and then you can go under it or over it, and you have different parameters, therefore different evolution.
Can I ask a down the road question? Is this a general theorem that chaos in 2 dimensions is not possible?
I don't know a general proof for it. I've never looked into that. I never really questioned it. So I was presented it. I was said that it's such, but I haven't asked that question. So yeah.
I think there is a theorem that states that there are only the solutions you mentioned for differential equations in 2 dimensions. Mm-hmm. So that's as far as there is a proof, I guess.
Yeah. Okay. Makes sense. So yeah, here we have the Lorentz system. So these are the 3 differential equations, 3 variables, x, y, z, and some parameters, sigma, rho, beta. So they describe, like I said, if you have a cold plate and a hot plate and like air or water, some fluid between them, you get convection currents. So they describe this. But one thing to note, actually, no one really uses it for convention much nowadays. And to the point that no one, it was very hard to find what x, y, and z were. They're not spatial coordinates. They are x is like the speed, you have temperature, and you have a certain term that determines the shape of your temperature gradient. So you can't actually see the attractor visually, but at least not in convection. And then you have, a few parameters, viscosity, temperature difference, and that. Rayleigh number is kind of the key parameter that's usually looked at when looking at the different shapes that the system can have. The other ones are usually kept fixed. And we are going to look into that. So, right, Lorentz attractor. So it has a lot of interesting properties. For a specific set of parameters, sigma, rho, beta, you can get chaos, like that. This is in 3 dimensions, so you can see it's kind of turned. And I mean, let's just kind of look into that. At it, you've probably seen this, but so you have the butterfly shape. So this is starting at a certain point. It evolves, and then it can go around on one for a while, and then it can go to the other one. As you can see, if it goes to 1, it'll stay there for a second. So you have short-term predictability, whereas in long-term, you don't know what's going to happen later. And you can see there's a red and a blue line, which started essentially identically together. And they have now spread further apart. We can make this a little more obvious. Not like that, but let's say this one. So wait. Well. So yeah, you have the red and the second blue line. They're kind of following each other, but very quickly diverging, so that you have exponential divergence up to the size of the attractor. So you won't have exponential divergence forever, but once they're maximally separated within the size of the attractor, you essentially stop diverging. And yeah, so that's the strange attractor. It's pretty strange, but probably nothing new. So yeah, I'll just mention some properties so we know them. So perturbations to initial conditions diverge exponentially, as I said. The exponents are, by the way, called Lyapunov exponents. So it's just a measure of how chaotic the system is. Phase space volumes, despite the divergence of any 2 points will diverge. If you evolve a volume, the volume will always contract to 0, actually. Because although the points will diverge, it'll while stretching, it'll be squeezing much faster. So eventually, it'll become exactly like flat. So yeah, things flatten out. So it's a dissipative system in that sense. Yeah, the tractor itself is, like I said, flat, so it doesn't have a three-dimensional value. And interestingly enough, as you saw, it has kind of two planes that it orbits in. And yeah, because like we said, it can't be two-dimensional. The plane it orbits in can't be two-dimensional, because otherwise you can't get chaos. But it's also converging to a certain flat shape. So it's not quite three-dimensional. So if you evolve it forever and then you have a Hausdorff dimension, its dimension is actually 2.06, apparently. So it's greater than 2, so you can have chaos, but it's just barely. So it's very weakly chaotic in that sense. And yeah. Oh, wow. I'll go quickly. Ooh, wait. Kind of halfway through. OK. Can I have like 5 minutes? Or is that 2?
0 minutes.
0 minutes, necessarily?
OK, 1 minute.
Ooh, OK. Ooh, OK. Sorry. I didn't see them before. OK, so we have a difference between the chaotic system on top and noise on the bottom. You can see it's predictable. By the way, if you plot the any peak relative to the past peak, you can see that that line, it's very kind of straight. So it's perfectly predictable. But anyway, this you can tell the difference of this by actually listening. So I have 3 sound files that are going to be played. So one of these is random noise. And the other 2 are low-order chaos. And they all have the same power spectrum. So the Fourier transform is the same. So it's just a phase difference. So I'll play 3 of them for you, and then listen to which one is out of. So try to figure out which one is out of place. And like write it down. Don't say anything, because we'll have like chain reaction effect. See if you can tell the difference. And yeah, OK. Let's try that. So that's 1. That's 2. OK. You all know what you want to say. Kind of. Decide which one is the odd one out. Yeah? OK. So now, who has actually heard the difference, obviously? Anyone? OK, in that case, who thinks it's the first one? No chain reactions. So if you think it is, just say so. OK, 1, 2, 3, 4. Second? Third? OK, it doesn't work. I guess you need a larger group of people. They did an experiment where they posted these 3 online. And like you heard, you can't tell the difference. Actually, in my class I took, they had a larger auditorium, and they did this too. But although you can't tell the difference, by kind of just guessing, sort of, you get it right. So a lot of people online answered it, and statistically, most people got it right. It's actually the second one, but I guess here it didn't really work. You need a larger sample size. 1 person was right. OK. Should I just flash through? You have
-2 minutes.
OK. Can I show videos? Yeah, OK, fine. OK, fine. You have it in turbulence, by the way. So yeah, you have deterministic aperiodic behavior with exponentially divergent perturbations. That's generally the description of chaos. Larger than 2 dimensions. Yeah, I guess we didn't talk much about Lorentz systems. But cool. Turbulence has strange attractors in it, just so you know. But yeah, here's a pretty picture. So you can see vortexes, and they mix. Topological mixing there. OK. No time for questions, or what?
Questions?
See the videos.
Thank you. Yes.
So you said the Lyapunov exponent characterizes how much chaos there is. Can you explain what that is a little more?
So you have, if you evolve a sphere, you will have, like I said, the volume will decrease. So some of them will be negative. So some of them will be shrinking, but some will be diverging. So you have, in a sphere, you have 3 dimensions. So Lyapunov exponents show how the 3 dimensions decrease or increase. So it's kind of an exponential fit to the size of, yeah.
Cool.
But, yeah.
You want to see the picture? Yeah, also, could you say a bit more about some physical systems? So I think you would have got to turbulence.
Yeah, so turbulence. OK, so by changing the Rayleigh number, you can have different behaviors. Like back just here. So here you can have either for small Rayleigh number, you just converge to 0 right away. For a little bit larger, you have 2 centers that it converges to, but there's 2 of them. Then larger, you have intermittent chaos, where it's chaotic and finally diverges to one of the centers. Then you have just pure chaos. So you can kind of see it in turbulence, although, like I said, it's not. So here you see this turbulent flow. You can see the 2 vortexes, and it's converging. There is no mixing, more or less. But that's kind of where this comes from. Then, yeah, this one, like I showed, you have the 2 vortexes, but so they start off converging, and then they mix together. So here you have chaotic behavior. And also in another one right here, I think they're increasing the speed slowly. So you start with no chaos, and you get into chaos. So you have vertices that converge. Then they're increasing something, or maybe just time. Then they start mixing out. Then you have those. Yeah, now it just gets crazy. Yeah, so you can see just transitions between the different states of the system.
So you can ask other questions later. So
yes.
there's nothing to speak again.